Hey everyone, just wanted to create a quick clarifying video on the concept of osmolarity versus tonicity. This is going to be a question that's hit pretty hard on the exam, so I just wanted to make sure that there's a sort of a short review session, or short review video rather, to make sure that everyone's on the same page, because both of these concepts have a lot of similarities, but also really important differences. So let's get into it. So the easiest way to visualize this, in my opinion, is to first talk about osmolarity, right? So osmolarity. So the best way to visualize it is to create this sort of tube system here. And this diagram is present in a lot of textbooks, and I believe in our textbook for the course as well. Actually, I think I'm going to make that just a little bigger so it's a bit easier to visualize. Sort of like this U-shaped tube. And typically in these examples, what we want to do is we want to assume that the middle of this tube has some type of a semi-permeable barrier. And we're going to say that this barrier is only permeable to water. And I apologize for my not so great handwriting, but I'll do my best. So we're going to assume that the barrier is only permeable to water. And on both sides, we're going to have a certain amount of water level. And within these barriers, we're going to have a certain amount of solute. So let's say that this is side A and this is side B. And side A, let's say it has, and this is just arbitrary, but 4 molecules of solute, right? So we're going to give it a concentration of 4 osmoles. And then on the right side, we'll double that and we'll just say, or not double, but we'll say it has 6. 1, 2, 3, 4, 5, 6. So what we can say here definitively in this statement, right, is that the osmolarity on this side, osmolarity of A is greater than the osmolarity of B. And how do we get there? Well, osmolarity is sort of similar to molar concentrations, except it takes into account the total amount of solute. So the total amount of ions that are suspended in solution. So what does that look like? For example, in some cases it can be really easy. If we have 3 molar of Na plus ions, that is equal to 3 osmoles, right? However, there comes a special caveat that if we have 6 molars of NaCl, remember, it's the total ion concentration, right? So all of the solutes that are suspended within a given solution. So we would say that this turns into, because it ionizes, right? It becomes an aqueous solution. We have NaCl, we have Na ions, and we have Cl ions. So we get 6 moles of Na plus ions, 6 moles of chloride ions. That would give us a total osmolarity of 12 osmoles. Because we need to make sure that we're taking into account the total ion concentration, not compound concentration. So that's an important clarifying concept. The second thing that's really important to understand is that osmolarity takes into account total concentration of all solutes, whether or not they affect, or whether or not they can permeate through the membrane. So oftentimes when we have a semi-permeable membrane, in this specific case, we're saying that this membrane is only permeable to water. But if we have another tube and we say that that tube, we can create that tube right here, for example, like this, and we can put another membrane in the middle. We can put some more water in the middle, like that. And let's say that this membrane is permeable, and we're going to say that these are ions, and then we're going to say that these, this is urea molecules, right? So typically urea molecules are able to pass freely through membranes. They don't need any type of a special protein or anything like that to move them through. They just pass through, diffuse through passively. Whereas ions, they typically need some type of channel. They're not really able to permeate, right? So if we have a bunch of these urea molecules, right, and we have all these ions, the osmolarity of each of these solutions, so both we'll call this A and B again. The osmolarity of this A solution is going to take into account all of these solutes, and this osmolarity of the side B is going to take into account all of these solutes. So let's say we have, 3 molar urea and 7 molar chloride ions. Our osmolarity for side A would then be 10 osmoles. Hopefully that makes sense and helps clarify the concept of osmolarity. So, how does this get different from tonicity? Well, osmolarity is a colligative property, right? It's not really dependent on anything other than the concentration of a given solute within a solution. So osmolarity in that sense doesn't change. Tonicity isn't necessarily describing the concentration of the solution. This is kind of where things can go a little bit different and things can get a little bit confusing. But tonicity instead is describing more so how water is going to be moving, or the effect that non-penetrating solutes have on water movement. So in order for us to understand that, it's first important for us to understand how water moves through these membranes. So let's go back to this diagram right here, the first one that we talked about, right? In this first diagram, we know that we have 4 osmol concentration on the left, and we have 6 osmol concentration on the right. Well, earlier we said that the membrane that's in the middle, it's only permeable to water. It's not permeable to the ions. So what's going to happen in this case is we know that things are always going to move from a low concentration, or from a high concentration rather, to a low concentration, right? So high concentration to low concentration. Well, typically what that would mean is that you're going to see movement of this high ion concentration to low ion concentration. Well, we can't do that, right? Because we just discussed the fact that the ions are not able to permeate through the membrane. So instead, what we're going to see now is that we need to think about this in terms of water instead, right? So where is the higher concentration of water? Well, higher concentration of water is going to be where there's less solute. So this has high H2O concentration here. We've got low H2O concentration here. So essentially what's going to happen is we're going to see net water movement from here to here. So that ultimately, because we know that concentration is some amount of moles over liter solution, right? We know that that's how we get our molarity solution. We know that's how we get our molarity. So we can decrease the concentration by doing one of two things. We can either increase the moles, right? Increase our numerator, or we can decrease our numerator, right? And the opposite is true. The opposite is true if we want to decrease our concentration. If we want to decrease the concentration of something, we either decrease the moles of it or increase the liters of solution, right? So in this case, we wanted to decrease the concentration on the right side. We can't decrease the number of moles because it's impermeable to ions. So instead what we got to do, we got to increase the total amount of solvent that's on the side. So we're going to see net water movement ultimately until we get, we're going to see when water moves through that there's going to be a rise in water volume here, right? Because we had water volume moved from the left side to the right side. And then we're going to move until we equilibrate our solutions to 5 osmoles on each side, and we get an equivalent osmolarity on either side. And the driving force for this is a term that you may have heard, may be familiar with. And apologies, I don't have too much space. I'm just going to try to work with what I have. But this driving force for water moving is what we call the osmotic pressure. Right? So this is a really important concept for us to understand. Now, this is the first video, and then in the second video, we're going to cover tonicity.